Welcome to this lecture on NPTEL course on radar systems. As we discussed that radar is a complex system. So, we engineers always try to understand any system by doing a model. That model we will discuss today. That model is called radar equation. So, it is a basic model of the whole radar system. Now, it is a very simplified model. There are various simplified assumptions in this model, and in the practical situation, the situation is somewhat different, and various assumptions that we make, some of them do not hold there, some of them hold there. So, but the beauty of this model is that it actually ultimately reaches that final real system by various modifying this model. So, we will see that today we are discussing this model at the starting of the course. At the end of the course, we will again revisit this model and we will make various changes in the assumptions of this model, and will be more realistic model will come up. So, actually that is the way by which all electronic systems are studied, or basically any engineering system is studied. So, we will start with the radar equation. So, what radar equation says, that there is a transmitter, that transmitter is giving the power, the RF power, and that is being radiated to the free space medium. Here it is an assumption that the whole medium is free space. There are no other scatterer etc. nearby, and we are this transmitter is through this transmitting antenna, a microwave antenna, it is pumping that power to the free space. You see the electromagnetic wave are going, it is also going in other direction, but you know the transmitting antenna, generally all antennas has a spatial gain. So, it will try to point to the expected zone of the target. So, more power is coming here compared to other directions. So, now it is there is an target. So, it is hitting that target. Then as you know that if any object, any target, if it gets illuminated by the electromagnetic wave, then if it is a metallic target, we know it will reflect, but some portion will still go inside up to the skin depth etc. But it is even in real metallic things, not an ideal metallic things, some portion goes inside, maybe some portion gets transmitted etc. But also what happens, the target absorbs the energy, and some of that energy it again emits as a source, that is called scattering. So, it is different from reflection, refraction etc. So, scattering, actually in radar we are interested in the scattering, because this scattering gives the inner information of the body, because here the target is behaving as a secondary source. So, some of the information about the characteristic of the target we get from that. So, that scattered energy is now coming back. It is also going in other direction, but depending on the target, it the receiver. So, this target also will have some gain type of thing. So, it is not that it is an isotropically radiating a thing, depending on its shape, size, material parameters. Some of the energy is in some of the direction is spatial direction is getting more angular direction is getting more energy compared to the So, whatever energy is coming, that is falling on this radar receiving antenna, this is a receiver. So, that antenna is taking that power and then putting it to the receiver, and receiver is measuring that received signal, that is called echo by radar people, and then various measurements that we have discussed, various functions of radar are taken care of by processing that echo. So, this is the model. Now, so we will say that mathematically, if we want to describe this model, let us say that transmitter that has a peak power Pt. here I am writing PT, but remember this is the peak power, because also there is an this model I am saying, though this model is valid for all types of radar. So, but we will try to understand it later by pulse radar, because that is easier to understand, though this model is valid for CW radar also and other type of radar also. Now, so the power radiated, power given by transmitter is PT. Now, that is given to the antenna. We are assuming here no loss of the antenna. So, generally microwave antennas are lossless. So, actually loss is very few. So, we generally neglect it. Now, that transmitting antenna, let us assume that it has a gain of GT. T subscript stands for transmitting side. Similarly, the power received by the receiver, let us call PR, and this receiving antenna, let us say it has a gain of GR. Okay. And this distance, radial distance from the transmitter to receiver, that distance, let us call this R, and so transmitter to target, and target to receiver, it can be different, as we have discussed earlier, that if it is a bistatic radar it will be different, but let us say R1 and R2 are the 2A. And now, target, when I say scattering, actually there is a parameter that we will discuss next, that is called radar cross section. Actually, radar cross section is some equivalent electrical area of the target. Please remember that this is not same as the geometrical area that we will see. Also, it is depend on which direction you are seeing from. So, because scattered energy in this direction is different from scattered energy in some other direction. Also, at which frequency you are seeing, it actually is a function of what is the shape of the object, what it is made of, what is the polarization of the waves that is transmitted, and polarization of the scattered wave, etc. So, on various parameters it depends, but the beauty of this radar cross section, it is a parameter for mathematical modeling of this system. We introduce this radar cross section. This is the characterization of the target. It is generally called sigma. Its unit is meter square, and in dB scale it is generally called dBSM. So, it is not the, again I am saying it is not the geometrical area, it is the electrical area that the receiver is saying in this direction, etc. So, now we can start having a mathematical model equivalent to this radar equation, that will be called equation. So, you see that transmitter is giving PT power in this direction of target. This target is far away from the transmitter. So, it is in the far field of the transmitting antenna. So, basically plane waves type of thing is illuminating the target. Similarly, the receiver is far away from the target. These are all assumptions of this model, that it is receiver is far away, and in radar that is mostly valid, because radar sees it at kilometer sort of distances, etc., several hundred kilometers. So, we can say that R1, R2 both are very large compared to the this dimension of this antenna, or the far field, which is 2d square by lambda, typically we call it. So, this. So, what are the then assumptions of this model? Let me write that one thing is there are medium is free space medium, no other scatterer than the target, okay. The target is at far field of transmitting antenna and also I can say receiving antenna. Okay. Now, if I so basically plane wave sort of illumination, this free space this target is far field, that means I can say that basically plane wave illumination. The first part, the target is at far field of transmitting antenna, that gives plane wave illumination of target, and the second part, that the receiver is at the far away distance from target, that means R2 is very large, that gives that the receiver is also getting plane waves scattered from the target. Okay. So, with these assumptions and this GT and GR, they shows the spatial gain of the target in this direction. That means, this transmitter and target, there is an angular direction. So, in that direction the gain is GT and gain function is GT, and similarly the target and receiver, they are at a particular orientation from the reference direction. So, in that direction this GR. If we do this, then we can write the we can relate the, knowing this from PT, we can find an expression for PR that will help us to connect this whole model mathematically, that we will do now. So, if I have a transmitting power PT and that is being radiated to free space by an GT. So, what will be the power intensity received by the target? Can I say that power intensity received by the target will be PT GT divided by 4 pi R1 square. Now, as I said that target intercepts this power and re-radiates or scatters the power in the direction of the receiver, and let us say that radar cross section of this target is sigma. Please remember that this sigma is dependent on the frequency of this transmitting source, it is the dependent on the angle that it is making, that means we call it aspect angle, then polarization of the wave, then also it is dependent on the material parameters of the body, that means mu, epsilon and sigma of the target. It depends on shape of the target, then it is a function of size of the target, etc. It is function of many things. Suppose I know that value is sigma. So, I can say that power scattered or power intensity, to be specific, power intensity scattered in the direction of the target, that will be PT GT by 4 pi R1 square into sigma. So, this is the power, that is this is the, it is not intensity. So, at this point I am writing that again in this direction powers that is scattered. So, power scattered, not power intensity here. So, what will be the power intensity at the receiver of the radar? So, since this distance r2 is very large, so it will be in the plane wave. We know plane wave is a spherical wave sort of, it is a approximation of the spherical wave at a large distance. So, so we can write that this intensity will be this power by 4 pi r 1 square into 1 by 4 pi r 2 square, because that variation we know from our basic electromagnetic understanding, that it is a plane wave falling. So, it will be like this. Now, this is the intensity, this is intensity, this is the scattered power. So, you can also say that this is the scattered power intensity at the receiver of the radar. So, we come to the next, that how much power now the receiving antenna will take. So, obviously, we know that it has a spatial gain. So, into this, but these again actually will be, so the receiving antenna, any antenna that also has an effective area, that is also an electrical effective area. So, we can say that power, let that, so that means here any antennas, its receiving characteristic is called, so let I am calling it AE. So, it is the effective area of receiving antenna. So, let me say now that AE is effective area of receiving antenna. Actually, this AE parameter is required for any receiving antenna. For transmitting antenna, I have not specified it because it is transmitting, but for receiving antenna we need effective area. So, already the power intensity at the receiver, or I can say at the RX antenna, because the antenna and the receiver, they may be at different places. So, it is basically at the receiving antenna, this is the intensity. So, what will be the power captured by the antenna? So, I can say the power captured by receiving antenna of the radar will be PT GT sigma by 4 pi r 1 square into 4 pi r 2 square into AE. And we assume that this again is a microwave antenna, lossless antenna. So, this whole power will be given to the receiver. So, I can say that power received by receiver of radar is PT GT sigma AE by 4 pi r 1 square into 4 pi r 2 square. So, this we know that from our, if we look at this diagram, we call that power received by the receiver PR. So, now we can say that PR is this. So, you see now mathematically everything is related. So, this is the radar range equation. Now, here people you can further manipulate this, but this is the basically radar equation. So, because this expresses what this whole block diagram express, the same thing is expressed here. So, this is the physical model, this is the mathematical model of the radar. This is called radar equation. radar equation. Now, we see we will just go on making some more assumptions, but those are specific to some radar, but this is the fundamental one, because the fundamental assumptions of this thing is that the whole medium is free space, though we know that in reality that may not be the case. No other scatterer than the target. Target is at far field of transmitting antenna and receiving antenna. You can also say that actually there is another assumption, that no loss in entire radar system. That means there are no loss in the transmitter, receiver, transmitting antenna, receiving antenna. So, this is also a lossless system. But you see that if I write like this, there is a spreading loss, etc., because that is why we are getting all these mathematical things. So, spreading loss is assumed in free space, because whenever a spherical wave goes, it has a spreading loss, that loss is incorporated. That is why this 1 by 4 pi r 1 square, 1 by 4 pi r square, that variation actually gives a loss, because as I go more and more, the power intensity is reduced. So, that is in the form of a loss, but that is not loss in the system. So, the lossless system is assumed for the radar. So, under these 4 assumptions, this radar range equation, where it is, this radar range equation, or someone is called radar range, why I will come just now, but it is a more correctly it should be called radar equation. Okay. So, this model we have seen. Now, you see that for any antenna, its transmitting gain G and its effective area A, there is a relation. So, J and A, they have a relation between them. That relation is, I think in antenna classes you have seen that relation is G is equal to 4 pi AE by lambda square, where lambda is the electromagnetic wave's wavelength, A is the effective area gain. So, we can express this receiving antenna's AE in terms of its own transmitting gain Gr. So, if you do that, that means just put this. So, you will get the expression for PR is that PT, GT, GR, what PT, GT, GR, sigma, then 4 pi whole square R1 square R2 square. Okay. This is one, that means this equation actually gives you this equation if you take this help of this. That is one thing we can do. So, this is another radar equation. Now, we can make another assumption that if we have a monostatic system, we have discussed this thing in previous classes, monostatic radar system, monostatic, you can say radar system. That means what? That receiver and transmitter are co-located. If receiver and transmitter are co-located, then R1 and R2, what was R1 and R2? R1 is the distance of the target from transmitter, R2 is the distance of receiver from the target. So, they becomes equal. If you do that, the radar equation becomes PT, GT, where is the last equation? Last equation was this PT, GT, GR, sigma square, lambda square sigma by 4 pi whole square r, or let us r1 r2 let us call it r to the power 4. Okay. So, this shows us that you see power received. So, this is again a radar equation, power received is proportional to fourth power, inversely proportional to fourth power of the distance. Now, this is a very severe, it has a lot of implication, because now we are saying, you see, in a communication system, when the receiver receives the power, it is just 1 by r square if receiver is far away from the transmitter in a communication system. But in the radar, actually it is a two-way journey, because the signal is going to the target is taking that and scattering back, and then again it is travelling the same path, that is giving a r to the power 4. That means, the power received by the receiver of the radar is very, very small compared to a communication receiver, whatever power it receives. So, the challenges here will be extract the information from that weak signal, and you know that actually we have assumed that there are no noise etcetera in the system, there are no losses etcetera, but when noise will be present, then the noise will be comparable to this received system. So, eliminating that noise, understanding that there is a signal, and then extracting that information, there are huge challenges for that. That we will see later, that is why the radar needs a much more sophisticated techniques than the usual communication systems. That is one. Another assumption we will see that generally in a radar is a costly system, and if you have a monostatic system, then why you, and you see the actually that we will see in your assignments etcetera, that the costliest part of the radar is the antenna. Though antenna is a passive device compared to transmitter, it seems that what I am saying, but actually you will see that the transmitter is a high power device transmitting, but the electronics is well developed there, whereas antenna that has various challenges. That is why making an antenna, that is the one of the it will say it is the most costly equipment, though it is nothing, it is some metals etcetera, but it is actually the main engineering knowledge is required to design these radar antennas. So, that is why people say that why we will have two different antennas, because that will add to the cost. Instead, we will use the same antenna, and we will try to use the same antenna and in the some extra circuitry, so that we can multiplex between transmitter and receiver. If we do that, then that means I am saying that same antenna, because when I am sending the signal, I am not listening unnecessarily, because that time I cannot listen also, because it is a huge power, it is getting transmitted, and there if I want to hear for that look signal, it is no meaning. That is why radar keeps its eye, keeps its ear closed that time, and when it stops sending, that is why it starts sensing or listens to the echoes etcetera. So, same antenna for both transmission and reception. If you do that, then I can say that GT and GR both are the transmitting gain of the antennas. GT was for transmitting antenna, GR is for the receiving antennas transmitting gain. So, they becomes equal. If it is there, then PR becomes PT GT square lambda square sigma by 4 pi square r to the power 4. So, this is another radar equation. Now, from here I can say I will be deriving various parameters of radar, basic parameters, and by that we will start getting an understanding of this. But you see that unless and until we have this model, we could not say that what will be those parameters, because now one of the parameter is radar is for ranging. So, what is the maximum range a radar can make? Now, that unless and until I have modeled this in a mathematical form, I could not answer, but now from this model I will be able to answer that. Actually, like that I can say that not only that what is the range, also how much power is required to have certain range, how much gain of the antenna is required given the power. All these questions now I can answer. Also we will see that when I am doing the measurement, I need to say with confidence that whatever I am measuring is correct. So, there are some ambiguity in measurements, any measurement has some ambiguity. So, there will be some ranges which are called ambiguous range, some ranges are called unambiguous range, etc. What is the minimum range, what is the maximum range. So, all these questions now I will be able to answer, because I have a model of the mathematical model of the whole thing. First a physical model, an engineering physical model, then a mathematical model, and now I will be answering that. That we will see from the next class. Thank you.